Okay, this is problem 523. It's actually pretty simple, similar to the one we just worked on, except we don't start with zero velocity. We start with the given velocity. So ultimately, what that's going to mean is that the arbitrary constant in the first integration is not going to be 0. We have newtons per second squared. Notice we also have t squared, so second squared divided by second squared is 1, and we end up with the correct units once we multiply everything out. So because this thing is initially moving, we have a negative force, meaning it's pointing in the negative x direction. The previous one had a positive force, and it was pushing it in their direction of displacement. So we solve for the acceleration, again, just through simple force equals mass times acceleration, solve for the acceleration. So we divide this by 2 kilograms, so we get negative 3 newtons per kilogram second squared as far as units. So as before, we take the definition of acceleration, instantaneous acceleration. In terms of the derivative of velocity with respect to time, we'll multiply both sides by dt. Plug in the value for the acceleration right here. And we get that. Okay, so then you can integrate both sides. The integral of dv sub x is just going to be v sub x. Here we can take the constant outside the integral sign, and the integral of t squared dt is t cubed. Plus, again, we add our arbitrary constant c. So we're going to use these initial conditions. V0, which is at t equals 0, is 9 meters per second. Here I just divided by 3, so I just simplified the constant. So we know that at t equals 0, the velocity is 9 meters per second. This term will go to 0 at t equals 0. That leaves us with c equals 9. So this is our general solution. This is our particular solution. So what do we do now? We take the derivative, the definition of the velocity in terms of the derivative of the displacement with respect to time. Multiply both sides by dt. Plug in our known value for v sub x, which includes this constant in this case. So we get dx is equal to v sub x, which is this thing, which is in the square brackets, times dt. So we integrate both sides. The integral of dx is x. Here we have 2 terms, so you just integrate these separately. This is a constant, so we can take that outside of the integral sign. Integrate t cubed, which is t to the 4th over 4. The integral of dt, or the integral of just a constant times dt is that constant, times t. And then we add our arbitrary constant again. In this case, the arbitrary constant is going to be 0 because the displacement at t equals 0 is x equals 0. So since we have this initial condition instead of before we had the initial condition for the velocity of 9 meters per second. So in this case, this c is 0. And so we get a particular solution. Now, the question was, when does this equal 0? Is that right? So part A was to find t when v sub x was equal to 0. We were moving at 9 meters per second. The question was, when did we stop? Stop means that the velocity is 0. So you take the value of velocity, in this case, not the displacement, but the velocity. And you say, okay, at what time is the velocity as a function of time equal to 0 meters per second. Because what's going to happen is going to go 9 meters per second, it's going to slow down until it gets to 0, and then it's going to go backwards the other direction. So I set v sub x equal to 0, and I solve for the t value of t where that happens. So if I subtract this from both sides, I'll get positive 1 Newton per kilogram second squared. T cubed equals 9 meters per second. Okay, divide by this constant. T cubed equals 9 meters per second. And what I did is I took the reciprocal of this. So the reciprocal of 1 Newton per kilogram second squared is 1 kilogram second squared per Newton. And this should end up have units of seconds cubed. So I think that's what I do next. Well, I say it's seconds cubed because it has to be. If I'm going to say the cube root of seconds cubed, I'll get seconds. But just to show you, if I start with meters per second times kilograms second squared per Newton, and if I substitute in for Newton, I put in 1 kilogram meter per second squared, I'll get meters per second times kilograms per second squared divided by newtons, which are kilogram meter per second squared. I take the reciprocal of this part here, which is second squared per kilogram meter. So I get meters per second, kilogram second squared, kilogram meter. Kilograms cancel out. One of the seconds cancels out with this exponent. Meters cancel out. All I'm left with is seconds squared times seconds, which is seconds cubed. So that's what I expected, so I'm going to do it right. So I take the cube root of both sides. Cube root of t cubed is t. I get the cube root of 9, which is 2.08 seconds. Cube root of seconds cubed is seconds. So that's the time it takes to stop. If you go any longer than this, it's going to start going back towards the left. So the second part asked, what happens after 3 seconds, I think, because 2 seconds is after 3 seconds. So all you do is you just plug in t equals 3 seconds. Actually, I know what they wanted to know is how far does it go. So you have to solve for time first, the time for it to go to 0 velocity. Then you use that time in the displacement equation to calculate how far it goes. So it has to go positive because it started at 9 meters per second. It's going, slowing down, it goes to 0, and then you're going to go the opposite direction. So if you plug in 2.08 seconds, time for it to stop, into the displacement equation, you get 14 meters. And then the final asked what was the velocity at t equals 3 seconds. It should be negative because after 2.08 seconds it's 0. So you plug that into the velocity equation. You get negative 18 meters per second. So it starts out at 9, stops after 2.08 seconds, and then it's really booking its way back in the other direction. After 3 seconds, it's negative 18 meters per second already. Okay, so that's it.